My name is Joshua Williams,
I'm Christian Psalms,
Uncle Terry's Harris.
and we're Group 3 for the Steam Engine Project in Thermodynamics 1.
The first part of this project was the history. This first steam engine was originally invented in 1698 by Thomas Savery with the intent of pumping water out of coal mines. The steam engine was first introduced to automated machinery in the workforce. But before that, we used water wheels and early wind turbines and horse or mule operated wheels, and that dominated the early workforce. But the steam engine made it more efficient and freed up labor for other industries in the early 18th century. Now, although we don't currently use the steam engine in its original form for any industrial uses, its daughters or its predecessors, no, not predecessors, the things that came after it, right? The gas engine and diesel engine have built America.
So, for the components in the thermodynamic cycle of a steam engine, you've got quite a few. For the component side of it, you've got your piston, your flywheel, your piston rods, your cylinders, your crankshaft, your crank rods, stuff like that. All of these parts work together with each other. So, if one does not work, then the whole machine can't work. They all have to work at the same time with each other in order for it to work. Um, to touch on that a little bit more, if your piston doesn't turn, then in order it doesn't push down on your piston shaft, it can't turn your crank, and when your crankshaft and your crank don't turn, then your flywheel doesn't turn. You can't convert that steam into energy or mechanical work. For the thermodynamic cycles of it, there's about 3 cycles that it goes through before it starts over the whole process. The first of which is an isobaric cycle, and this is simply just when heat is added to water in the boiler. Once that water's heated up, it then goes to the second cycle. This is an adiabatic process, and this is when the water is actually converted to a high pressure steam, and that in turn, once that steam hits that cylinder, it starts to expand. Once that happens, it pushes against your piston, which then that leads us into the third cycle. The third cycle is a polytropic cycle, and this is pretty much just when the excess steam in that cylinder is then pushed against the piston, which in turn turns the engine. Once that happens, if it were to not push against that piston, your cylinder would basically just explode. It couldn't take it. It's got to have a way to get out, so that's how it does it. Um, so there's that. Similarly, even though that's how a real one works, our 3D printed engine works in the same manner. The only difference is we don't have a boiler, so we had to substitute that high pressured steam for just pressurized air out of an air compressor. Just kind of some things like that you're going to have. Other than that, though, the processes work the same. And after that third polytropic process, they all start over again. Whereas in your boiler, it would start the process over. In ours, we don't have a boiler, so simple solution for that is just to push more PSI, pressurized air through our engine and let it run.
For the overall prototype build, our group faced many challenges in both printing and constructing our engine model. This forced us to find ways in which we could be proactive and construct our working model. Included below are pictures of the 3D model in the actual report.
All right, so the next part is prototype challenges. So while we're designing and slicing the files to make this or to 3D print this, we came up with several issues. So first off was deciding how much filament material do we use to make each part. We decided on around 15 to 20% for the large parts and around 100% filament rate for all the smaller parts because they still have pressure put on them, but they're so small we were worried about them just shattering. And then once we went to go print them, the first time the crank bushing didn't and the shaft, they both did not print out correctly. So we had to reprint those. And then they were just not designed correctly, so we had to go and work on that as well. So also, we ran into the issue of supports. In all the holes, there has to be supports to hold the material up and thus create the hole. We had issues removing those supports and so that the steam engine would work correctly.
So for the construction issues, as Josh said, there was many issues in the actual production of our pieces to construct, such as the 3D printing errors, stuff like that, where the 3D printing machine just didn't want to work with us or with our files for whatever reason. On the construction side of it and putting those pieces together, there were many more errors, as Josh mentioned yet again. The files that we had sliced and everything, some of the dimensions were wrong. It wouldn't be due to that, our parts couldn't align the correct way. We had to kind of improvise ways to do it. For example, in our piston, we had to drill a small guide hole into the piston rod so that we could stick a rivet in there that would allow the piston rod to connect at the right length within our piston, so that when the piston turned, it could then turn all the rest of the parts of the engine.
During the testing phase of the steam engine prototype, we encountered several issues that needed to be addressed. Leaks were a significant problem, compromising the system's efficiency and safety. Alignment problems emerged, causing mechanical parts to malfunction and wear. Maintaining consistent air pressure was also a challenge that it affected the overall performance of the steam engine.
Teamwork and time management was also an issue in the beginning. So, as mechanical engineers, we didn't have too much free time on our hands. So, we decided to divvy out the project in different parts. So, my job was to find the files, slice the files, and print them out. And then Christian and Q also helped with that and making it run. And they also did a good bit of the report as well. Of course, I did the history and some of the other issues that happened during the development of our steam engine.
So for the future improvements, the big one just goes back to, as we mentioned multiple times in this presentation, the 3D printing part of it. If there was a way for future engineers that have to do this project, if there was a way that they could figure out the right dimensions on their files to check those to be sure if they're safe for the right filament, making and also just having a way to make sure the machine is doing what you want the machine to do. That's a big one we ran into. As Josh said, having to reprint some things and stuff like that because our machine just wouldn't do what we wanted to. And we, as Josh also said again, we're so busy, so we would leave it at times to print it by itself when we'd be in class or doing homework or whatever. And even though we'd be in the same building, we weren't directly watching it. So I would just say maybe for future improvements wise, make sure your files are correct so that you can hopefully and correctly do it on the first time and not have to worry about reprinting things. And also just having a little bit of time divvied out and divided between your group to watch over the actual machine and 3D printing part of it to make sure that everything's going correct.
For the results and discussion, the steam engine prototype worked, but not without overcoming several key challenges. We faced issues with selecting the right screw types, which we resolved by standardizing the screws and ensuring capability. The problem with the material in the 3D printed parts was resolved by refining the printing process and incorporating thorough post-processing steps. We produced air pressure. We experimented with different nozzles and air compressor settings to achieve the desired air compressor of 50 psi and ensure efficient air exits.
Thank you.
Thank you so much.